All right, I think now's a good time to go ahead and get started. Emily, can you hear me okay?
Yes, I can hear you.
Excellent. So let's go ahead and kick things off. So first of all, welcome everyone. If you're returning, thank you for coming back. And if you're new, welcome. And I'll just do a quick brief of CSNP and pass it over to Emily, who's our speaker for this evening. Um, So if you were able to attend our relaunch back in October, then you know a little bit about the new direction CSNP is heading towards to. And if not, it is on YouTube. Check it out. But in a nutshell, we are a nonprofit organization focusing on cybersecurity education. We when it comes to resources and contents that we put out there, it is all free, right? So there's no membership fee. We strongly believe that in order to make cybersecurity accessible, that it does has to be free. Essentially, we can't help people if they can't access our resources, right? So everything that we try to do, we try to make them free. So please support our organization, donate, partner with us. If you want to speak, we have not opened a speaking portal as well as a volunteer portal just yet, but those will be coming very soon. So if you are interested in volunteering or speaking in future events, we will send out emails. So if you have not already joined our community, go ahead and do that. That's the best way to stay up to date as to what we're up to. Our LinkedIn, Meetup, and of course, in our website. So, about the leaders shaping the future of cybersecurity, just a quick overview. Santosh, Curtis, and Elaine are leading our engineering departments as well as our education department. So part of what CSNP is trying to do with this new direction is build technology that's going to support our community, and that's you. So when we say our community, we mean individuals um, who are part of our network, and as well as businesses, small and mom pop shops, as well as nonprofits. So we are trying to build resources tailor for you because we do understand that when it comes to cybersecurity, a lot of resources that exist today are more tailored towards enterprise security or enterprise organization. So we're trying to do our best to change that narrative a bit. And with all of the amazing work that our engineering and education department does, we have the individuals who are amplifying our mission, the individuals who are making sure that the work that we're doing does not go unheard. And last but not least, to make sure that we do become sustainable, right? That is something that we are working towards too. And by sustainability, what we mean by that is supporting all of our mission initiative, our programs. And Shri is an individual who is leading that part of the organization. And before jumping into tonight's event, I forgot to introduce myself. My name is Abdel. I'm the executive director of CSNP as well as co-founder. And tonight's event is Emily Stamm. She is also a co-founder of CSNP. She more operates today on the board level. But today, Emily is going to talk about post-quantum cryptography. So I'll pass it over to her to introduce herself.
Thanks, Abdel. Hopefully I don't lose my voice. Let me share. Can everyone see my screen?
Sure can.
Great. So, hey everyone, thank you all for coming tonight. As Abdel mentioned, I'm Emily Stamm, and this talk is on post-quantum cryptography. And I gave a similar talk a couple years back, but since then there's been a lot of exciting updates in the field of cryptography, so I'll try to touch on some of those. So about me, I am a lead cryptography applications engineer at Niobium. Niobium is a startup that builds hardware for fully homomorphic encryption, or FHE, which is a new type of cryptography that allows you to do computations on encrypted data, and it is quantum secure. So I'll touch on FHE a little bit at the end, but I'll focus more on general post-quantum cryptography. I'm also the co-founder of csnp, cybersecurity nonprofit, which Abdel just gave a nice introduction to, that provides accessible cybersecurity education and awareness. So the agenda for today, I'll start out at the beginning with just the basics of cryptography. Then I'll lead into quantum computing and the quantum era. Then finally, I'll get into post-quantum cryptography and touch a little bit on the mathematics in lattice-based, which is the most common. Then I'll dive into some of the real-world implementations like Apple's iMessage that are using post-quantum cryptography. Then I'll talk about how organizations can prepare to transition their cryptography. And finally, a brief introduction to FHE. So first, we'll start with the basics of cryptography. So cryptography, from the Greek kryptos, meaning hidden, and graphen, meaning to write, translates to hidden writing. And cryptography has evolved a lot over the years. Some consider hieroglyphics from thousands of years BC to be an early form of cryptography. Then there's ciphers like the Caesar cipher from around 50 BC. And that's where you shift every letter over by a set amount. For instance, a shift 3 would have A going to D, B going to E, and so on. And then the person would get this message that looks incoherent and shift it back over to decrypt it and get the original message. And then over the next thousands of years, cryptography evolved a lot. There's the famous Enigma machine, which was a lot more complicated cryptography. In a sense, what these more complicated cryptography things do is the same thing, but they scramble it a lot better to make it more secure. So of course, the Enigma machine was broken by the Allies, and that was a big part of World War II. Then we move on to the 70s, where the first public key cryptography algorithms were created. So for thousands of years, we've been doing what's called symmetric or secret key cryptography, because there's just one symmetric or secret key. So things really shifted with the public key cryptography, because for instance, with the Diffie-Hellman key exchange, it allowed you to create a secret that no one else knows among multiple parties in a public channel. And this is pretty amazing if you think about it. That's like saying you walk into a crowded room, you start talking to a stranger, everyone's overhearing your conversation, but you're able to come up with a shared secret that no one knows. So it's pretty powerful. And elliptic curve cryptography, as well as RSA, are some other forms of public key cryptography that have become popular. And then AES, or Advanced Encryption Standard, is really the standard for symmetric cryptography. So in a sense, it's very similar to the Caesar cipher, but much more complex so that it's harder to decrypt. So today, cryptography is a lot different than it was many years ago. Today, cryptography really means secure communication in the presence of third parties. So some of the things that cryptography provides are confidentiality, which is restricting the access of information, integrity, which is verifying that data has not been altered in transit, either maliciously or accidentally, and authentication, verifying the identity of a party. And to accomplish this, there are three main types of cryptography that work together to achieve these different things. So there's symmetric cryptography, which I mentioned, where there's just one secret key that is used for both operations, such as encrypt and decrypt. Then you have public key cryptography, where there's a public key and a private key. So there's different keys. And the public key can be known to anyone, but the private key can only be known to usually one party. There's also cryptographic hashing, And that's a function that maps data of arbitrary size to data of a fixed size. And it does so in a way that satisfies certain properties, such as it's very difficult or impossible to reverse the hash, which is the output, and get back what you originally put in. So what makes cryptography secure? So there are three main things that are especially true for public key cryptography. One is the key secrecy. So the key is a secret piece of information that's used to uncover or reveal information, or sometimes to authenticate or provide integrity checks of information. So the key is the secret piece of information that you need to keep private. And this might sound pretty simple, but this is actually can cause huge problems, especially in organizations that are managing many keys, that each key has different parties that have access to it. So it can get very complex. The next is hard math problems. So the strength of these cryptography algorithms relies on some underlying math problem, where if you can solve this math problem efficiently, you can break the corresponding cryptography. And then there's proper implementation. So once you have the algorithm and you generate your secret key, to do all this, you also have to actually implement the algorithm. And the implementation can oftentimes leak information. And this might not seem to be a big deal, but even very subtle information leaks, like checking whether the padding is correct, for instance, a very simple check. Leaking that information can actually be devastating to the cryptography. So it's very important that these three things keep cryptography secure. And if you're an attacker, generally what you're going to do is attack one of these three areas. You'll either obtain the key somehow, you'll solve the math problem, or you'll take advantage of an implementation. And in general, attackers usually go towards the key or the implementation because the math problems are very hard and have been studied for many years and gone over and have security proofs of them. But today with quantum computing, we're going to be actually talking about attacking the hard math problems themselves, so the actual algorithms. So I'll give a brief overview of public key encryption and digital signatures. So here we have Alice and Bob, and Alice wants to send a message to Bob. So Bob creates a public-private key pair, and he gives the public key to Alice. And he could give this to anyone. Anyone could get this public key. That's okay, because all this public key can do is encrypt. So she takes this public key and encrypts the message and sends it to Bob. Now, Bob has the corresponding private key that only he knows, so he can actually decrypt it and get the message back. So this is one way that you could share a secret. Alice could generate some secret and then share it with Bob. There are other mechanisms that are a little bit different called key exchange or key encapsulation mechanisms. And for the purpose of this talk, I'll use public key encryption and these key exchange. I'll use those terms interchangeably because they generally accomplish the same thing, which is getting a shared secret among multiple parties. Now let's say that Alice wants to send that message, but she wants to make sure that Bob knows that message is coming from her and that no one tampers with it while she's sending it. So this time Alice generates the public-private key pair. And Alice gives the public key to Bob. Anyone can have the public key. But she uses the private key to sign the message. Then she gives the message and the signature to Bob, and Bob uses the public key to verify that this digital signature corresponds to this message and corresponds to this private key. So digital signatures, again, very important for authenticity and for integrity. So digital signatures and public key encryption or key exchange, those are two of the main aspects of public key cryptography. So where is public key cryptography actually used? So it's really used all over the place. Basically, anytime two or more parties, and parties can be anything, could be two endpoints, could be people, could be a server and a client. But anytime two parties want to communicate securely, they need to use public key cryptography. So an example of this is HTTPS, which anytime you go to an HTTPS website, it's using public key cryptography. And hopefully most of the websites you go to are HTTPS because the S stands for secure. Blockchain and cryptocurrencies also use it, especially the signatures. The Internet of Things, Secure Shell, VPNs, they all also use public key cryptography. So now we'll dive into the quantum era. So quantum computing is this new form of computation that harnesses properties of quantum physics. So if you think about what we call classical computers, those are basically any computer, your phone, your laptop, a supercomputer, they all have a bit as the fundamental component, and that bit is 0 or 1. And it represents a two-level classical system that can be one thing or another. But a quantum bit or qubit represents a two-level quantum system. So it can actually be in any combination or superposition of these two states. And quantum computers go beyond that and they take advantage of quantum properties like entanglement, for example, which makes two different qubits kind of correspond to each other, where interacting on one qubit directly affects the state of another qubit. So quantum computers harness these properties to do computation in a completely different way. So it's not just doing computation faster, it's actually doing them differently. And in this different way, you can actually use it to do certain tasks more effectively than you do with classical computers. So what is the effect on cryptography? So Peter Shor invented Shor's algorithm, and this is an algorithm that uses a quantum computer to factor efficiently. So why does that matter? Well, RSA, one of the most popular public key cryptography algorithms that does asymmetric encryption and digital signatures, relies on the hardness of factoring. That's the underlying math problem, being able to factor a number into two primes. So Shor's algorithm can break RSA. And it turns out that the other public key cryptography algorithms, which are actually all just instances of a more general underlying math problem called the abelian hidden subgroup problem, they're all really different instances of it. And you can use variations of Shor's algorithm to break Diffie-Hellman, elliptic curve cryptography, basically all our current standards of public key cryptography. So this quantum computer does not yet exist that is powerful enough to run Shor's algorithm. Quantum computers do exist. We're into the thousands now of physical qubits, and it's very difficult to tell when we'll actually get a quantum computer that's powerful enough, because there are a lot of different factors, from the quality of the qubit to the type of qubit to error correction. So it's very hard to gauge when we'll actually reach that point. But we are quickly accelerating in quantum computing, so it's definitely important to take seriously. And another thing that attackers are doing is what we call harvest now, decrypt later attacks, where they're actually harvesting encrypted information because they know in 5, 10, 20 years, whatever it is, they'll have a quantum computer and they can use it to decrypt it. So this is very important for information that has long-term value. And then people often ask, how will public key cryptography affect blockchain? So the blockchain structure itself doesn't seem to be broken by quantum computing. It doesn't seem like quantum computers can break that. But they can break the digital signatures that blockchain uses. So blockchain will also have to update their cryptography. And symmetric cryptography like AES will be weakened but not broken. So we can increase the key size of AES and still be okay. But that's not true for the public key cryptography. So people often interchange the terms quantum and post-quantum cryptography, but there is a difference, and I wanted to make that distinction. So quantum cryptography actually uses quantum mechanics for the secure data transmission. It harnesses quantum properties to do this securely. And what's really amazing about this is that it has provable security, unlike public key cryptography, based on the laws of quantum mechanics. So it's provably secure, which is pretty incredible. And here, for example, is the Mesius satellite that China launched in 2016, showing a quantum key distribution over many kilometers. The problem is that it relies on expensive specialized hardware. There can be a lot of practical challenges, and it won't integrate easily with our existing communication infrastructure. So the problem is that quantum computers will break our current public key cryptography, and quantum cryptography is not really practical. So the solution is post-quantum cryptography. And post-quantum cryptography is cryptography just like our other public key, just like RSA and ECC, except it's based on harder math problems that we believe with strong evidence are secure against quantum attacks. So now we'll dive into post-quantum cryptography. So how do we create post-quantum cryptography? The first thing we have to do is identify hardness assumptions that are not broken by quantum computing. So factoring was a hard problem, we assumed, but that's clearly not true when it comes to quantum computers. So we need to find new hard math problems. And we can't just find any hard math problems. There's a lot of different kind of properties that these math problems have to have in order to be good for a crypto system. And once we've identified a good hard math problem, we then have to actually build a crypto system based off of this hard problem. Then we have to do security proofs, which show that with strong evidence, this crypto system is secure against quantum and classical attacks. And then we actually have to evaluate the scheme. So we have to evaluate it for its efficiency, for how easy it is to use, for potential side channel attacks. So there's a lot more you have to evaluate the scheme. Even if you have a working crypto system, if it's not efficient, if it's not fast, or if it has huge key sizes, nobody's going to want to use it. So I think it was in 2016 also that NIST launched their PQC, or post-quantum cryptography standardization competition. And I think they had close to 100 algorithms that were submitted. And through several rounds, this was narrowed down. And recently, I think within the last year, NIST decided on certain algorithms to select for signatures and for encryption/key encapsulation. So for the digital signatures, they selected crystals dilithium as the main one, which the type of math problem it's based on is called lattice-based cryptography. And it was also rebranded as MLDSA. They also selected Falcon, another lattice-based cryptography that has different trade-offs in terms of efficiency. And they also selected Sphinx, which is not as efficient, but they wanted something that wasn't based on lattice cryptography. So this is based on hash-based cryptography. And then there are also some other digital signature algorithms like XMSS, LMS, HSS that actually were standardized years ago. The thing is that these are stateful digital signatures. And that means that we have to keep track of a state to use them. And that's very problematic in general. It's very hard to keep track of a state. And if you do it wrong, if you mess up, it can be devastating to the cryptography. But it does have applications, like there's a blockchain, quantum resistant ledger, or QRL, that uses XMSS. So blockchain is a good example of something that can benefit from stateful hash-based cryptography. But for most examples, we'll probably be using more of the crystals dilithium. And then for key exchange, crystals Kyber was selected, MLKEM, and it's similar mathematics to crystals dilithium. And there were also several other algorithms that are code-based, so based on error-correcting codes, that are entering a fourth round, so we can have, again, that diversity in terms of the type of math problem. And they're actually also having another competition for additional digital signatures, and they just released a list of, I think, 14 digital signatures that made it to the next round, and still too many to really dive into at this point, but hopefully within the next couple of years, we'll have even more digital signatures standardized. So now I'll talk a little bit about lattice-based cryptography. Because lattice-based cryptography, right now, it's really dominating in the post-quantum cryptography field. Lattice-based cryptography, it's also being used in, for instance, fully homomorphic encryption, identity-based encryption, these other types of post-quantum cryptography as well. So lattice-based is a great one to start if you're interested in learning more about post-quantum cryptography. And a lattice is essentially a grid, so you can think of it as an infinite grid, except that instead of 2 dimensions, we're actually looking at it in hundreds of dimensions. And also in cryptography, where these infinite grids are actually finite because we put them over finite fields or rings. So we actually are looking at a finite mathematical object. But again, it extends in maybe hundreds of dimensions. And so an n-dimensional lattice can be defined by a basis of n vectors that generate it. And this basis is not unique. So for example, for this lattice, we have these 2 vectors that generate it. And what that means is that any point on this lattice can be reached by adding combinations of these 2 vectors. So for instance, this point right here is just twice of this vector. And this vector would be 2 up and 1 over this one. But here's another basis. This basis also works, but it's clear that it's not as nice to work with as this one. And that's where we get into the notion of a good versus a bad basis. And a good basis has short vectors that are nearly or actually perpendicular. And a bad basis has vectors that are not close to being perpendicular and they're longer. And a lot of lattice problems are very easy to solve if you have a good basis, but hard to solve if you have a bad basis. And some crypto schemes are based around that fact. So there are many hard lattice problems that cryptography is based off of. One hard lattice problem is the shortest vector problem, which is pretty simple. You're given a basis and you have to find the shortest vector in the lattice. One of the most common problems in cryptography is the learning with errors problem. And you can see that this is essentially solving linear equations, excuse me. This is essentially solving a series of linear equations, except you have this error, this noise, because solving a system of linear equations, that's easy. But you're given A and you're given B in this equation, and you want to find S, but you also don't know what the error is. And that's what makes it difficult. And so again, learning with errors, this is the basis for a lot of different crypto schemes. And here are some examples of some libraries. I can also email out a list. I have not tried all of these, but there are implementations of post-quantum cryptography. I also included Zama in the corner, which does fully homomorphic encryption, if anyone's interested in that as well. So now I'll dive into the real-world implementations. So one is Apple's iMessage. So Apple adopted the PQ3 protocol, which they defined, And it uses Kyber, which again is that key exchange that was selected. And it uses that in tandem with elliptic curve cryptography. And this is very common right now in cryptography. We're using classical cryptography and post-quantum cryptography. That way we know we're at least classically secure and hopefully post-quantum secure as well. And this is often called hybrid encryption. And Signal actually, before Apple, also did a post-quantum cryptography protocol. But Apple improved upon this by doing rekeying, which is where you repeatedly derive new session keys. And I would also say that the reason that Apple and also many of these applications are focused on the key establishment, the key exchange, and not the digital signature is because, again, of that harvest now, decrypt later. Adversaries can't go back in time and mess with data or pretend to be someone else. So really the main risk right now is with key establishments. Google also, in their TLS protocol, they also implemented post-quantum cryptography. Again, MLKM, same algorithm. Although there were some users that experienced connectivity issues, it wasn't exactly because of the cryptography, the post-quantum cryptography. There were some updates that needed to be made. But that is something they implemented. AWS also has cryptographic protocols you can use. There's secure shell, there's secure file transfer, and these also use that same algorithm, the Kyber or MLKEM. And again, they use it with elliptic curve cryptography. There are also a lot of blockchains that are using quantum resistant cryptography as well. I mentioned QRL, one of them earlier. Ozone chain seems to be one of the most popular that's using post-quantum cryptography, but there are others. And again, it uses that selected scheme, the crystals, Kyber, and dilithium. So now we'll get into how organizations can actually transition to post-quantum cryptography. So the first and most important thing likely is to increase cryptographic agility. So cryptographic agility or crypto agility is the ability to quickly and seamlessly transition to new cryptography algorithms. And this could also mean new implementations. This could mean different key sizes, but just being able to quickly transition your cryptography, which a lot of organizations, especially older organizations, they have cryptography algorithms hard-coded, and it's very difficult to actually switch algorithms. You have to go back and even rewrite code in some cases. So having crypto agility, being able to quickly transition your cryptography is very important in this age, because while we're fairly confident in our post-quantum algorithms, they've been studied for over a decade, we still don't know for sure. It's not really provably secure like quantum cryptography. So it's important that we be able to switch cryptography or even implement multiple different algorithms and be able to switch between them in case there is a new attack that comes out. Another thing they can do is perform a quantum risk assessment. And with this, they can really look at what cryptographic algorithms are used, what key sizes, what data or communication is being protected, and are there any constraints on the algorithms in use. So really looking into where your cryptography is used, what is used, because that will be really important to know so that you can plan how to transition it. The third thing they can do is identify long-term data. So this goes back to that storing our encrypted data to decrypt later. Things like intellectual property, social security numbers, that will be relevant in 5, 10, 20 years. Again, we don't really know. This is very important to already be encrypting. But other data like credit card numbers or information that's going to become public soon, we don't have to worry about that as much. We can deprioritize it. Then organizations can develop their transition plan. And there's a lot that goes into transitioning cryptography. Again, a lot of times these larger or older organizations, it's a lot more complex. There's a lot more they have to figure out in order to develop this plan. So that's very important. And then organizations can also start testing the standardized algorithms. We already have algorithms that have been selected for standardization. So we can already start to use these algorithms and test them out. Then another thing organizations can do is update their policies. So they update their policies to reflect the quantum resistant measures, and especially new implementations, it's vital that they be crypto agile and support these post-quantum algorithms. Then organizations, once they're ready, can deploy the algorithms, probably in phases. And again, focusing on data that has the highest level of long-term value, that's probably where you want to start. And then, like all software, you want to monitor the implementations, stay up to date on any new attacks that happen, and identify any weaknesses or vulnerabilities in your specific implementation. So lastly, I'll get into PQC and beyond, which is really just a way of diving into fully homomorphic encryption for a moment, because that's what I do for work. So fully homomorphic encryption, it actually allows you to do computations on encrypted data. So we have cryptography for data at rest. That would be AES, for example. And we have protocols for data in transit. That would be TLS. But there hasn't been cryptography for data in use. And FHE actually provides cryptography for data in use because you can use the data without even having to decrypt it. And this will especially be important in applications like machine learning, being able to do machine learning on encrypted data without ever having to decrypt it. So it'll open up a lot of possibilities of applications and also hopefully just make things more secure. And again, it is post-quantum, it is lattice-based cryptography. A lot of it is based on those learning with errors problems, variations of that. And the problem with FHE right now is that it's still fairly slow. We can try it out and we can use it for smaller applications, but at large scale, it can still be difficult. So right now, organizations are working on improving the software, improving the hardware in order to get this so that we can actually use it at a large scale. So in conclusion, we talked about cryptography and how it ensures communication, secure communication in the presence of third parties. Quantum computers harness properties of quantum mechanics, and in doing so, they can break our current public key cryptography. But post-quantum cryptography is cryptography that also runs on our current computers, but is conjectured with strong evidence to be secure against quantum and classical computers. So, thank you.